Finding derivatives. This is a basic technique of calculus. The derivative of a function at a point a f of a is the slope of the tangent line of the graph of the function at a f of a. That's all it means. This basically gives us the slope of the curve. To find the slope of the tangent at a f of a, find the slope of the chord with a f of a as 1 point and a and an arbitrarily small h, f of a plus an arbitrarily small h as the other endpoint of the chord, and then let h become very small by taking the limit as h approaches 0. So tangent line is approximated with the limit as h approaches 0, f of a plus h minus f of a over a plus h minus a. To generalize for any x, that is, at a point where f of x has a derivative, and not all functions have derivatives everywhere, we must avoid sharp points or missing values and so on. The derivative of f of x is found by taking the limit as h goes to 0, the limit of f of x plus h minus f of x over x plus h minus x. That would give us an expression or a function. The derivative is a function of x, and we could plug in a specific value to find at a specific x what the slope might be. To give a visual of this, let's take a curve. This is black right here. And so we would look at the curve, and we're interested in the tangent line, which is right here. We would take chords on each side, the red on the left, the light green on the right. And as we get smaller and smaller h's, so we start looking at less and less length in the chords, we start getting very close to the tangent line with the slope. That's what we mean when we say the limit as h goes to 0. As h goes to 0, the chord starts looking like the tangent line. Notice h can be positive or negative. For a derivative to exist at a f of a, the limit of f of x as x approaches a must exist. You can't have something that does not have a limit. Something like an absolute value even, where the graph goes down on one side and up on the other with a sharp point. There is no derivative at the point at which it turns around. And the function must be continuous at x equal a. So this implies that f of the limit as x approaches a of f of x must be f of a. It's more common, after understanding the theory, to use known derivative forms. For example, the derivative with respect to x of f of x equals x squared can be found using the limit formula. The limit h goes to 0, f of x plus h squared minus x squared over x plus h minus x. We would expand the x plus h squared to x squared plus 2xh plus h squared. Then we would cancel the x squares in the numerator, and we would cancel the x's in the denominator. We would then factor the h out of the numerator and cancel with the denominator. We get 2x plus h. The limit as h goes to 0 of 2x plus h. Well, if h goes to 0, that leaves us with only 2x. The formula that we would use is the derivative with respect to x of x to the n is n x to the n minus 1. Well, in this case, when n equals 2, the derivative with respect to x of x squared is 2x, 2 minus 1, or 2x to the first power. The derivative gives the rate of change of a function, such as velocity being the rate of change of displacement. The slope of the tangent line at a point gives the slope of the function at that point.